We live in a universe with 3 dimensions of space and 1 of time. Up, down, left, right, forward, back, and past and future. 3 plus 1 dimensions. Or so our primitive Pleistocene-evolved brains find it useful to believe. And we cling to this intuition, even as physics shows us that this view of reality may be only a very narrow perception. One of the most startling possibilities is that our 3 plus 1 dimensional universe may be better described as resulting from a space-time 1 dimension lower, like a hologram projected from a surface infinitely far away. The holographic principle emerged from many subtle clues discovered over decades of theoretical exploration of the universe. Over the past several months on Spacetime, we've seen those clues. We've built the foundations needed to glimpse the true meaning of the holographic principle. We've moved from quantum field theory to black hole thermodynamics to string theory. We've made a background playlist if you want to start from scratch, and I especially recommend catching last week's episode. But this is tough material, so let's do a review. The story started with black holes, and with Jacob Bekenstein, who derived an equation to describe their entropy. A black hole's entropy represents the amount of quantum information of everything that ever fell into it. This Bekenstein bound represents the maximum possible entropy/information of any volume of space. Oddly, that maximum is proportional to the surface area of that space, not its volume. And that was surprising. Surely the information in a volume of space depends on that volume, like 1 bit per infinitesimal voxel, not 1 bit per pixel on the surface. Stephen Hawking confirmed the Bekenstein bound by calculating the amount of information leaked by a black hole as it evaporates in Hawking radiation. His discovery of Hawking radiation led to the black hole information paradox, because this radiation was expected to erase the quantum information of everything that fell into the black hole. But destroying quantum information would break the foundations of quantum mechanics, hence the paradox. This conundrum inspired Gerard 't Hooft to show that the information of all material that fell into the black hole could be imprinted on that outgoing Hawking radiation. And while it's waiting to be radiated, that information should be encoded on the event horizon of the black hole. Nice solution, but new paradox. Things that fall into a black hole do actually experience crossing the event horizon and being inside the black hole. So the interior of the black hole has a dual existence. From the point of view of outside observers, its contents are smeared into 2D on that surface, but from the POV of anyone falling in, they are definitely inside the black hole, plummeting to their doom in full 3D glory. This is the first glimpse of a holographic spacetime, a 2D surface that encodes the properties of the 3D interior. 't Hooft, along with Leonard Susskind, extrapolated this to propose that not only is any surface sufficient to describe the locations of all particles in its volume, but also the full machinery of that volume can exist on the surface, all degrees of freedom needed to describe the behavior of everything within. But it's one thing for this stuff to fit on the surface, but how is it actually encoded? How does the 2D surface store information about that extra dimension? And how do interactions on that surface correspond to interactions in the volume? Leonard Susskind laid out the first steps to how this could be achieved using string theory. But ultimately, it was Juan Maldacena who figured out a concrete string theoretic realization of the holographic principle with ADS-CFT correspondence. But I'm getting ahead of myself. Let's ignore string theory for the moment and just think about how to create an extra dimension. Let's say we start with a plane, a flat 2D spacetime. Now, grid it up into a lattice of cells and make a set of rules about how those cells interact with each other. Those rules are a field theory. The lattice itself is the field, and the cells are some elementary component of the field. But perhaps they're not the smallest possible component. For now, let's just say the size of those cells depend on how we're looking at the grid. For example, the resolution of our microscope or the power of our particle accelerator. Probably, the rules between cells, the field theory, depends on their scale. Focus on a very small scale and we see a very fine grid that interacts according to one set of rules. Zoom out and we see a coarser grid with cells that are the average of smaller cells, but which presumably interact via different rules. Or so you'd think. But we're going to add something weird. We're going to say that our field theory is scale invariant. We'll say that the rules are the same for small pixels or big pixels. We see this scale invariance in fractal patterns where the rules defining structures repeat to infinitely large or small scales. We also see it in string theory, which I'll come back to. A field theory with this property is called a conformal field theory. In the last episode, I said that a conformal transformation is one that leaves all internal angles unchanged. A conformal field theory has this property. For example, you can change the scale at every point on the grid separately and not change the internal angles or the shapes of the pixels, which corresponds to not changing the rules of interaction. By making this conformal field theory, we've added asymmetry, invariance under local changes in scale, also known as Weyl invariance. This adds a degree of freedom everywhere, like a new infinite number line at each of the 2D grid points. Objects on the 2D grid also have values on that number line. They exist at a certain scale. If objects at different scales don't tend to interact with each other, then this new degree of freedom behaves like just any other dimension. Our 2D grid behaves like a 3D volume, and we can treat it like one, at least mathematically. You might say it's not a real 3D grid because the third dimension is fake. But is it? What is a dimension but a number line of possible values which A, exists alongside the other dimensions but is independent of them, B, over which the rules of physics stay the same, and C, imposes some kind of locality. For example, elements of that number line need to be next to each other to interact. Crudely, this is how an extra dimension can be coded in a holographic universe. But for the details, we need string theory. Even from the beginning, string theory had hints of this scale invariance and dimensional weirdness. The first iteration of the theory, around 1970, tried to model the strong force between pairs of quarks, mesons, and this strand of gluons that behaves like a vibrating string. A nice feature of this model is that changing the length of the strand, which defines the energy in the bond, doesn't change the basic physics. That means you can pretend string length/energy is a separate dimension as a calculation trick. The weird thing is that when you write the quantum wave equation for the gluon strand with length expressed as a separate dimension, you get the wave equation of a graviton, the quantum particle of gravity, which is ridiculous given the puny energy scale of the meson. Gravitons shouldn't even exist there. This and other glitches led to string theory being abandoned as a model for the strong force, but it was quickly rejigged to make it a theory of quantum gravity, and the scale invariance of the strings became a central feature of string theory. Fast forward a couple of decades to the 90s, we now have several versions of string theory that try to explain how vibrating strings can lead to the familiar particles of the universe. These were tentatively united by Ed Witten's M theory, which showed that different types of string and string theories were all related by dualities. A duality is when two seemingly different theories prove to represent the same underlying physical reality. These arose from the way string size and energy scales could be rescaled. But the strangest string duality was still to come with ADS-CFT correspondence, proposed by Argentinian physicist Juan Maldacena in 1997. Strange because it provided the first concrete description of a holographic universe. Maldacena imagined a set of string theory objects called brains. These are like multi-dimensional strings that can serve as start and end points for strings, but also as spaces embedded within higher dimensions. Meldocene are considered geometrically flat 3D branes. These branes are extremely close together, basically overlapping. The strings connected to these branes are scale invariant, so their length and energy can vary without changing the physics. Under certain assumptions, he found that the resulting brainy structure looked just like a Minkowski spacetime of 3+1 dimensions on which there lived a field theory that arose from interactions between branes. In itself, that field theory wasn't stringy, rather it was a quantum field theory like the ones that give us our standard model of particle physics, a Yang-Mills theory, but with supersymmetry added in. It was also a conformal field theory, a CFT, so it was invariant to the scaling of grid sizes. This quality came from the energy scale invariance of the strings embedded in the construction of this space. In good old string theorist style, Meldocene defined a new spatial dimension that incorporated that invariant scale factor. The 3D space became a 4D space. While the original space was flat, the new space had negative curvature. It was a hyperbolic anti-de Sitter or ADS space. The conformal field theory in the original space included no gravity, but in the higher dimensional space, gravity emerged, revealing a full quantum theory of gravity. This is the ADS-CFT duality. As with the other dualities in string theory, this one was extremely useful for calculations. When interactions in the lower dimensional field theory are extremely strong, we would say the fields are strongly coupled, then the corresponding higher dimensional gravitational structures would be weak and solvable. Conversely, strong gravitational fields in the higher dimensional space, like in black holes, look like solvable configurations of particles in the low D space. Among other things, this provided a new resolution to the black hole information paradox. The information lost in a black hole persists perfectly comfortably in the lower dimensional space. And the techniques of ADS-CFT correspondence are even extended to disparate fields like nuclear and condensed matter physics. But the more startling implication of ADS-CFT is that it's the first concrete realization of the holographic principle. The lower dimensional CFT space is the surface of the ADS space because the field theory exists where that new dimension becomes infinitely far away. That's tough to imagine. So let's go back to our depiction of an infinite hyperbolic space from the last episode. Represent a 2D hyperbolic plane as a compactified map, and it has an edge, at least a mathematical one. Anyone inside the hyperbolic space still has to travel infinitely far to get to that edge. Now, stack many maps to represent slices in time. The resulting column has a geometrically flat and finite surface that is a spacetime all on its own. The rules of interactions between cells on that surface is a quantum field theory, but those rules translate to interactions in the volume, in the bulk, where it's a theory of gravity. ADS-CFT is a hint that we may live in a holographic universe. Now, ADS-CFT doesn't represent this universe because our universe doesn't appear to be negatively curved ADS space, nor does it have 4 spatial dimensions as in Meldocene's calculation. But there are efforts to generalize this to a universe more like our own. The question we now wrestle with is this. A series of mathematical clues indicate that our universe may be holographic, or at least have a dual representation in a lower dimension. Can these just be crazy mathematical coincidences? Maybe. But perhaps our familiar 3+1 universe has an alternative, perhaps a more true representation out there. An abstract mathematical surface infinitely far from our location and from our intuition, projecting inwards our familiar holographic spacetime. Before we jump into comments, I want to let everyone know that there's new merch in the merch store, including the return of our Game of Thrones inspired shirt, The Heat Death of the Universe is coming. It's a great way to support us, as is joining us on Patreon, links in the description. So, last week was the warm-up to today's episode, in which we looked at how infinite space-time can have a finite boundary. And first up, no psychedelics were involved in making that episode despite what people thought. The universe is just that weird. A few of you asked whether our perceived universe is just the surface of a higher dimensional space. So that's actually the opposite of the proposition behind the holographic principle, which suggests that our perceived universe is the volume, but it can be encoded on its lower dimensional surface. In ADS-CFT correspondence, the volume exhibits gravity via a type of string theory, while the surface exhibits no gravity, only a quantum field theory similar to the field theory behind the Standard Model. Part of the confusion comes from the fact that Maldaceno's derivation is for a volume with 4 spatial dimensions, which would then have a 3D surface. So obviously that doesn't directly correspond to our universe, but there's work to generalize it to the case of a 3D volume with a 2D surface. Related to that, Musical Ways asks whether, according to ADS-CFT correspondence, can we say that there would be no gravity on the surface of the 2+1 Minkowski spacetime? So first, the surface in the current ADS-CFT spacetime is 3+1, 3 spatial, 1 temporal dimensions, as I just mentioned. That surface contains only a conformal field theory and no gravity. The strange miracle of ADS-CFT is that gravity arises naturally when you add the extra spatial dimension, which ends up looking like the volume contained by a 3D surface. KI9 asks whether the things we learn from ADS-CFT are applicable to our universe, given that our universe doesn't have negative curvature. Well, we don't know for sure that it doesn't have negative curvature, just that any curvature, negative or positive, is very weak compared to our current ability to measure it. Measurements of the geometry of the universe indicate flatness, but we may never know whether it's truly flat or just flat as far as we can see. Several people were offended that I dissed Chronicles of Riddick. Well, I want to be on record as saying that Pitch Black was an artistic masterpiece. Real Mammal summarizes my position well. Chronicles is the 3rd best Riddick movie, but is still better than any Marvel movie. And I'm sure saying this will cause no further comments. Kualito notices that it's looking more and more likely that Roger Penrose might literally be a Time Lord. In a separate comment, Midplane Wanderer states that Sir Roger Penrose is an unsung wizard. So apparently we can't agree on what genre Roger Penrose belongs to. Personally, I've always thought of him as a Jedi Master, especially with all of that dubious quantum consciousness stuff, midichlorians, microtubules, potato. Anyway, perhaps we need to accept that Penrose is beyond genre, like if Gandalf had a TARDIS and a lightsaber. By the way, if anyone feels like drawing Roger Penrose dressed as Gandalf with a lightsaber and a TARDIS, you would win the internet.